Hi, welcome everyone. Welcome to this course, Introduction to Statistical Mechanics in Soft and Active Matter Systems. So far we have discussed different things like random noise, uh, uh, one day random walk, random flights, and its different applications to different problems. And we discussed, uh, you know, uh, Brownian motion in great detail, a free Brownian motion, and Brownian motion in the presence of some external potential, namely, first we did it for harmonic potential, and then we also did it for any generalized potential, and then we got to know about Lagrange equations, and we formulated the generalized Lagrange equations, and we uh, solved it, and we have seen the fluctuation dissipation relations, and we also formulated the generalized for fluctuation dissipations from relations. Now our main the last part that is remaining is like how we are going to see these things in in continuous probability space, because it is related to probability and all these things. So Brownian motion is like Brownian particle in that media, it diffuse, right? So to do that, what we will do, we will talk about the diffusion equations, and we will calculate the diffusion probability for different cases, and we will get to know, because this diffusion equation and the applications to it I think in this kind of soft and active matter systems, it plays a role. And also, like normal diffusion process where like Brownian motion is involved, that is called passive systems, because there is only, that is, diffusion is related to the thermal fluctuations and how that is done. So basically we will do that, and we will see that how these probabilities that will evolve with time, with space, how it moves, and we will derive different things related to the diffusion equations. Okay, so let me share my screen. Okay, so let me start the discussion here. So basically we will do for different systems where we, that will be involved in, we will in will we will see how this different diffusion processes will will be involving different things. Okay, so first, this is a grand chapter talk the so diffusion equation we will study. Okay, so so basically diffusion is a process. So diffusion, what is diffusion? Diffusion is the process by which an uneven concentration of substance gets gradually smoothed out smoothed out spontaneously. So there is no forcing, it is happening spontaneously. Okay. Okay. So the observation of pure diffusion is not simple as it seems, because sometimes there can be different processes that can dominate the mixing of different things. Let's say convections currents which sort of set up by small thermal gradient that actually facilitate this mixing or diffusion, and advections due to initially present velocity gradient also can be something. Now this macroscopic a macroscopic description description of the process of diffusion process of diffusion can be given on simple physical situations. Okay. And it is it is mainly based on fundamental partial differential equation, and that equation is called the diffusion equation. So now I will say that how it is connected to Brownian dynamics. So basically here it serves this diffusion equation serves as a basic model as a basic model of phenomena that exhibit dissipation. So this is first term that is familiar to our earlier discussion, which is a consequence of irreversibility irreversibility of macroscopic systems in time. Okay. So basically if we, so this is, we are talking about concentration, we can also think about like the probability of finding a particle. It's like the same thing, right? So let's say instantaneous instantaneous concentration, or like probability of Brownian particle, finding a Brownian particle satisfies, like probability satisfies the equation of continuity. So we studied this equation of continuity in fluid mechanics and all these things. So which is called in this constant, which is called Fick's first law. First law in this context. So now we first denoted this Fick's first law. So what is that? That del rho del t plus gradient of g is 0. This is Fick's first law. So here rho is probability and rho is a function of space. So rho is a function of space and time. This can be also like probability density and like this. Okay, so this can be thought of as probability density and like this. And J is probability current density. So this can be think of as like probability is uh, is conservation of probability. So this Fick first law, so equation 1 is a simple statement of probability conservation. Okay. Okay. So now we will further assume a second thing. We further assume that current density J is proportional to proportional to the local difference in probability or concentration. So here concentration or probability is like the similar thing. So that means we are talking about J, which is a function of R, and T is some constant, let's say D, gradient of rho R T, right? This is called Fick's second law. So first law is from the continuity equation, and second law where we are defining the probability current density, probability current density with the probability density. Huh? So this D here, the positive constant D is called diffusion constant. Diffusion constant. And now this minus sign, what does it indicate? This negative sign indicates negative sign indicates indicates the fact that diffusion occurs from a region of higher probabilities, higher probability density or concentration to a region of lower probability density. So higher probability density to lower probability density. That's why the diffusion current sort of makes this thing even out. Huh? So now if you substitute this thing into this, then it becomes del T of rho RT is equal to divergence of, so this will be minus gradient J and minus minus plus, so this will be D of rho RT. This is constant, so it goes out and it becomes Laplacian of gradient is divergence and gradient will be Laplacian, it will be rho RT. Equation 3. This is equation 2. Yeah. Now here if you look it carefully at left hand side, it has a first order differential equation in time variable, and here it has second order differential equation in spatial variable. So now let's write few things about this equation. Equation 1, sorry, equation 3 is a parabolic equation, in the standard classification of second order partial differential equation. So in order to find an unique solution, what you need is, in order to get a unique solution, you need the specific initial probability density, probability density, let's say rho or t. Initial means t equal to 0, so t equals to 0, as well as well as the boundary conditions, the boundary conditions that specify this probability density at later time, that means t greater than 0. And so here we will see different things, because it is important, because we in our physics background sometimes we neglect the mathematical rigor. That now the presence of the first order time derivative in the diffusion equation implies implies this fact that the equation is not invariant. That means it changes. It doesn't in it does vary under the time reversal transformations, like if t becomes minus t, it changes, right? That means irreversibility irreversibility is thus built into this description of phenomena, description in the description of this phenomena. Now we will spend few times to understand this linear response or this linear behavior of this. So we will discuss the remarks on linear response. Now, in broad terms, in broader perspective, in broad terms, linear response, linear response means that under suitable conditions, suitable conditions, the average response of a system to an applied stimulus, to an applied stimulus or force is directly proportional, is directly proportional to the stimulus. So if the stimulus is more, response will be more. So the average here refers to the averaging over fluctuations at the microscopic or molecular level. So here average means average over the fluctuations at the microscopic level. Okay. Now here in this case, the linear response, the linear response implies that the diffusion current that we defined earlier using Fick's law, the diffusion current is proportional to the gradient of rho. So if the gradient of rho is more, the current will be higher. That means it is not the gradient of a nonlinear term of rho, that means rho to the power alpha, where alpha is greater than 1. like this kind of thing we actually, this kind of equations we have seen where uh, this is similar to like the heat equation where we talked about heat, how that diffuses in the system, right? Now a system's response need not be, need not to be remaining in linear region for a any, for any magnitude of the stimulus. Okay, let's say you are increasing the stimulus and you are increasing after certain value, that response is not linear anymore. So then at that point when it is not linear, then these descriptions fails. Okay, that means that's why we need to talk about, so these equations is valid only this that regime where it is uh, sort of linear in response. Okay, okay, now let's find the general solution of diffusion equation in d dimension. So if you know the general solution, then our calculation or descriptions or our understanding will be much more, simpler. Okay, so now let's say, so we talked about the random walks and all these things. So now to find the diffusion equations, let's say for probability, let's say we sort of, let's change rho r t to prt. It's just for the notation purpose. It is not any, like you can use any notation, because this, like the diffusion equation was applicable to any kind of systems where there is some gradient or no gradient, but here we are talking about only probability density, and this solutions is the general solution of that equation. Okay, so basically that equation becomes then del p r t dt is equal to d Laplacian p r t. This is equation 4. Okay, now first we understood that we need to specify some initial condition for this. So that's why we will use so the, so first thing first is natural boundary conditions. So the natural boundary condition is the probability density, you know becomes 0 at the boundary of this system. Let's say when r tends to infinity, along any directions, along any direction, this should be 0. Let's say initial, talk about a initial condition. Okay, now this initial condition is like when it is starts at t is equal to 0. Initial condition, let's say p R 0, let's say this is a d-dimensional R. Okay, so it starts at R. So here it means that this process starts from origin. It can also be written as like this, it can be written like this, it can also be written like this, where let's say it starts from a special position R naught. So we can always do the coordinate transformations, and we can get this R naught as to be the origin of the coordinate system. So now what happens that so it is a sort of kind of a delta function kind of says that at initial point it starts from a point, right? It's a certain point source. Okay, so that's why we are not losing in generality, because that R naught, which is starting point, it can be made to be origin of the coordinates in that system. And so the solution that we will obtain is called the fundamental solution of the grain functions of the diffusion equations. So the solution we will obtain is the fundamental solution or grain function. Okay, so so basically this diffusion equation presents an initial value problem. So let's to solve it, let's use Laplace transform. Let us use then let us use the Laplace transform. Now that is with respect to time variable. With respect to time variable. Okay. Okay, so then so and Fourier transform Fourier transform with respect to spatial variable. So for time variable we are making Laplace transformation and for the spatial variable we are making Fourier transformations. Let's say then let's say PRS is the Laplace transform and phi kt is Fourier transform of this variable P R T. Okay. And now, so from we are, you know, changing the variable from space using Fourier, and time to, from time it is Laplace. But let's connect this Fourier transform and Laplace transform. Let's say further, let's say phi ks denote the Laplace transform. So please be careful, like be attentive that how we are going to, you know, sort of solving it step by step of phi kt. So we are again sort of taking the Laplace transformation of Fourier transform. Okay. Now if you take the Laplace transform of this equation 4 of both side, then it becomes, for del t there will be, if there is a function of t, one will be s. So if you get it, so the Laplace transform of equation 4, that will be s p r s minus p r 0 is equal to d of p r s. Okay. So this is equation 5. Now we know this guy is PR naught, this guy is PR naught, we denoted here. So PR naught is delta D on this. So if you just then, you know, shuffle this together, then it becomes S minus D Laplacian of PR S becomes PR naught, that becomes delta D of R. Okay. So always see, there is D means there is dimension. Huh? Now expand this term in the Fourier space. Huh? Now expanding expanding P R S in a Fourier integral. Fourier integral, what we will write is Fourier integral with respect to special variable r, special variable r. Then we can write P R S is equal to, so two dimensional, it's d dimensional, so there will be 2 pi to the power d integration of ddk e to the power I k dot r phi k s. So this is the how you can to expand anything in a Fourier integral. So if you do this, then k becomes r. That's it. Okay. So what will be the delta function's Fourier transform representation? Now delta of dr has Fourier well-known Fourier representation delta dr is 1 by 2 pi d ddk e to the power I k dot r. Now if you use these equations like 7 and 6 into this 5, we can get easily. So it will be so s minus d sigma square. If you do this thing like not sigma square, Laplace square, so this is uh, special special versions. So here from special versions you will get 2ik, right? So for s it will be s. So delta 2 of PRS will give you ik squared 1 by 2 pi. So it will this there will be del r. So there will be first del 2 del r 2. So ik and then again ik. So ddk divided by ikr phi ks. Now if you use it, so this will be minus k square, there is minus d, so this will be dk square. So using 6 and 7 in equation 5, we get s plus d k square, right? So what we have done, we have written the equation in this, and then we are equating the coefficient of the basis vector e to the power I k dot r. So we are equating this with, so this is the differential part, this is this phi ks is the coefficient for this equation. So if you write this, then it becomes phi ks, and for delta functions it will be only 1, this will be 1, right? And from here you can get phi ks is equal to 1 by s plus d k square. So this is equation number 8. So now you have got the Fourier transform and Laplace transform form. So now we have got the double transformation. Now to get the probability distributions, we must transform back to the real means time and position variable, right? So what we will do, remember, it is easier to invert the Laplace transform first and then the Fourier transform. So first change the Laplace transform, then the Fourier transform. So we know the inverse Laplace transform of this fellow, like S plus A inverse, is e to the power minus at. So A is constant. So here there is S plus dk square. So dk square is constant. So we will do that. So then phi kt, which is Laplace of phi ks, then becomes e to the power minus dk square t. So our okay, so this is our equations. Now if you write this, then PRT then becomes PRT, then we have to just reverse transform it into this thing. Okay, so we know how to write this PRT. We have written the now if you want to get the Fourier transform, so the Fourier transform of this will be from K to R. From K to R, you have to do this from K to R. So now PRT then will be 1 by 2 pi to the power d to the power d dk e to the power I k dot r e to the power minus d k square t. So let's say this is equation number 9. Now what here becomes that a d-dimensional integral factors into a product of d integrals if you write it in r and k in Cartesian coordinate. Okay. Okay. So you can sort of solve this. So basically d-dimensional integral factors integral factors into a product of d integrals upon writing r and k in Cartesian. So you can always do the Cartesian coordinate transform. Cartesian coordinates. Okay. So if we do for one dimensional, we will get it for d dimensional. Okay, so basically if we do it for one coordinate, it will give you for another coordinates, right? Hmm. So k square actually, let's say it's k square, actually kx square, ky square, kz square, like this in Cartesian coordinate. So we can write it as I is equal to 1 to d ki square. So now for one dimension, so if you so this integral will be for two d dimensions, so d dimensions, so we will get p rt as 1 by 2 pi, let's say d1k ddk d1k, which also written as, let's say, dk1 e to the power I k1 r1 e to the power minus d k1 square t times 1 by 2 pi dk2 e to the power I k2 r2 e to the power minus d k2 square t dot dot dot, so dot, and last term will be 1 by 2 pi into dk3 e to the power I k3 r3 e to the power minus d, sorry, let's say this is d kd square t. So if we solve for 1, we will get d times of this, right? So basically let's solve it for 1. Let's solve it for 1 by 2 pi dk1 e to the power I k1 r1 e to the power minus d k1 square t, where this is from minus infinity to infinity, right? This is, so if you solve it, so let's write it in terms of this thing. So this whole term we can write it as 1 by 2 pi minus infinity to plus infinity dk1 e to the power I k1 r1 minus d k1 square t. Okay, so this is in k1 square, so let it write this term in some square fact. Okay, so let's say dk1 square t minus I k1 r1 becomes root dt k1 whole squared minus 2 times root dt times I, let's say, let's write it in this way. So let's write it in this way, root dt q1 times I by root dt 2 root dt, I by 2 root dt, 2 cancels out, root dt cancels, k1 times r1. So this term plus this is square I 2 root dt r1 whole square plus r1 square by 4 dt. Now this term, this guy can be written as an integral form, right? So then this becomes root dt q1 minus I by 2 root dt r1 whole square plus r1 square by 4 dt. So from here did I miss something? I hope not. Mm, So basically what we are writing is this term as like this. Huh. So right, so see these equations one more time, and then we can sort of go into this. So you can do in this way, or you can do like this. So you can sort of, you have to write in terms of whole squared, and you need to, so there must be, okay, so this is on sort of a shifted Gaussian. So we come back to this. Okay, so now this is this whole thing. Now if you substitute this thing, and let's say this is alpha q1 minus beta r1. Okay, so if you substitute this thing, then it becomes 1 by 1 by 2 pi minus infinity to infinity dk1 e to the power minus, this is dk1 square t, so there is minus, so minus alpha q1 minus beta r1 whole square times e to the power minus r1 square by 4 dt, right? So this is on some type of a Gaussian, then this will give like this, or you can use the other things, huh? So basically here this is one kind of a so this will give, So if you use minus infinity to infinity dA dz e to the power minus alpha z square, so this will give root over of pi by alpha. So here alpha is root dt, so this will give 1 by 2 pi into alpha is root dt, so 1 by root dt, right? Yes. So alpha z square, so alpha is alpha square here, this will be root dt times root pi times e to the power minus r1 square by 4 dt. So that makes it 1 by root over of 4 pi dt times exponential of r1 square 4 dt. Now you will get this kind of d times of this. So for this is for 1, there is d times. So basically if you get, then PRT becomes, PRT as a whole becomes, so PR of t then becomes 1 by root over of 4 pi dt. This will be d times time e to the power minus 1 by 4 dt into r1 plus r1 square plus r2 square dot 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 rd squared, and this becomes 1 by 4 pi dt times d by 2 into e to the power minus r square by 4 dt. So this is the main expression of this. This is the main solution. So this is equation 10. Now you can solve this equation also in this way. Let's say the shifted Gaussian integral. You can directly write this. You can directly write this. So that will be minus infinity to plus infinity dx e to the power minus ax square plus bx, that would be root over of pi by a times e to the power b square by 4a. For this is for real a greater than 0. So here if you see, there b is ir1, right? So this will be ir1 whole square, this is minus r1 square by 4a. So 4a is here dt, that's why 4 dt. Okay, so a was dt, so 4 dt. Okay, so sort of we got this expression. So this is the fundamental Gaussian solution. So equation 10 is the fundamental Gaussian solution to the diffusion equation in d spatial dimensions. So that we are getting fundamentally, huh? So this three-dimensional version is, we know, so now let's observe equation 10. First thing first, this solution equation 10 is function of r only. Okay, in the I'm talking about the spatial these things. If we consider only the positional dependence, now it has some consequences along with this. Okay, what are those consequences? First, the basic reason is that the diffusion equation diffusion equation involves the scalar operator, this one, which is rotationally invariant, rotationally invariant. And the second thing is the initial condition and boundary conditions, they are spherically symmetric, right? They are spherically symmetric. Okay, so that's why this is only there is only dependence of r there. Okay, so that is crucial. Okay, now let's see few things. Let's discuss few things first. So let's say an arbitrary initial distributions. For an arbitrary arbitrary initial distribution. So if the diffusion equation is for any arbitrary initial distribution, what that will do? So if now if arbitrarily specified probability distribution function at any instant at any initial instant t prime. If we know that, you can get that, probability distribution functions. So for a general arbitrary specified probability distribution function, which is shortly named as PDF, at any instant time. If we know that is at t prime, then we can write p or t at later time. It will be ddr g of r t, where r prime t prime is the initial thing, and that is the initial distribution. So if you know the initial distribution, you just need to know the green function, where t is greater than t prime, and g r t r prime t prime will be 1 by 4 pi 1 by 4 pi d t minus t prime whole to the power d by whole to the power d by 2 exponential of minus r minus r prime whole square divided by 4d t minus t prime. So this is the general for any general solutions. This will be this thing. So basically, the probability distribution function at any time or any further time t, which is greater than t prime, is an integral transform of the probability distribution function at the earlier time t prime, and the kernel of the transform is just the fundamental green function for the diffusion operator. So the kernel of the transform for PDF at later time given PDF at earlier time is just the fundamental green function for diffusion operator del t minus d That is what is this G stands for. So this kind of kernel is also there, and like for the heat conduction equations, for heat conduction equation this is called heat kernel. So this kind of things is there, huh? So now let's calculate the moments. There we will see some interesting things. Okay, so let's discuss moments of the distance traveled in time t. Let's calculate that. So any moment is calculated, r of t is calculated as dd of r p r t, right, for first moment. Now you can see this is the first moment, because here PRT does not depend on any angular coordinates. So this will become 0, because this is mean displacement mean displacement of diffusing particle. Because if you write r, there is some angular, this is a vector, so there will be the angular coordinates. So the integration over the angular coordinates will makes will makes will make it 0. Now, so all the moments actually calculated, all the moments okay, so all the moments can be calculated as using this formula r to the power L of t is equal to ddr ddr r to the power L p rt. So this is, so since it is distance, so then it becomes 0 to infinity dr d omega d rd plus L minus 1. So this is a volume element, right? This is volume element d omega d rd to p of rt. So d omega d is solid angle element, solid angle element in d-dimensional space, d-dimensional space. Now this, in this thing there is no angular coordinates, so from here we can immediately carried out the integration that, so this can be done, this can be done separately, right? So let's use this formula as 30. Now this solid angle becomes SD of 1, which becomes 2 pi d by 2 gamma function of d by 2. This is a good exercise you can do. See, this is the surface area of a sphere of unit radius in d-dimensional space. This is surface area of a sphere of unit radius in d-dimensional space. So basically now if you use Gaussian integral r to the power L, so then it becomes r L of t, then becomes, there is only thing becomes here r L p r t, right? Then for that, now this 2 pi d by 2, so this thing will give you gamma d plus L by 2, and at each point there will be 1/2, each point there will be 1/2. So this pi d by 2 from here, this will cancel out this pi d by 2. Okay, so only thing remains, so if you do this integral, then it becomes 0 to infinity dr 0 to infinity dr to the power minus r square by 4 dt into r t plus l minus 1. So from here you can write in plus 1. So this becomes gamma of d plus l by 2, and there is alpha 4 dt times 4 dt into half. So that will be this integration, because you know 0 to infinity x to the power n, sorry, dx x to the power n e to the power minus x square alpha x square, that makes it alpha alpha to the power n plus 1 by 2, that will make it d plus l by, sorry, that will make d plus l by 2, n plus l by 2 into gamma n plus l, so n plus 1 by 2 into half, so that half will be here. Now if you use it, then if you use it, so d plus l by 2, that will cancel out this d, pi and pi cancelled out, and half cancelled out. So now using these two things, you make, so then so here then it becomes 2 pi d by 2, 2 pi d by 2, 2 pi d by 2 by 2, okay, and then 4 dt 4 dt 1 by pi d by 2, 4 dt d by 2, 4 dt d by 2 cancels out, so this becomes 4 dt l by 2, and d plus l by 2 into d by 2 cancels. So only thing remains gamma, this is gamma function, d plus l by 2 times d by 2 4 dt times l by 2. So this is equation number 15. So from here you can see that moment moments grow, which is r l t, that grows t to the power l by 2. So now if you take the variance, then variance of r, which is r square average minus r average, this is 0. R square average becomes small r square average, so this becomes 2d 2d. So here use 2 plus, this becomes 2d d plus 1, so there will be d plus 1 by 2, and that will d by 2 plus 1, that means there will be 1d only. 2d times dt, because there it will be gamma d plus 2 by 2 into d by 2. Here it becomes, and this is 4 dt, becomes d by 2. So d by 2 times 4 dt, that becomes 2 dt dt. So this is like the simple Brownian motion. For 1d this will be 2 dt, for 3d this will be 6 dt, like this. Okay, so we'll stop here and we will continue our discussion in the next class.